We're going to work through the PICUP exercise set 2 body gravitation, and you can go ahead and open it over here if you'd like. We don't actually need this. I've got all the relevant information, but you can at least see the exercise set over here. So we're going to go ahead and look at the orbit of the Earth around the Sun by calculating the gravitational force on it and then updating position and velocity to animate that motion. So here is my code box. Let's go full screen. All right. So here I've defined some constants, 1 year, current time. One of the nice things is that we can go ahead and use real world units so we don't have to scale things down. VPython will scale things so they fit the screen. So if you're dealing with something that's on the atomic scale or on the solar system scale, the view over here is going to be scaled by VPython to fit everything. So first thing we need to do is notice that there are some comments in here. The comment is denoted by a hashtag. Any text after a hashtag is ignored by VPython on that line. And so it's really a good idea to get in the habit of adding in comments, something you'll want to train your students on. So I've defined 1 year. I'll use that in a couple of places, so it's handy to have that available as a variable. I need to initialize that current time for when we start going through that animation loop. And then here's that time step size, which we may want to play around with just to see what sort of effect that has on our results. So the first thing I need to do is to calculate an initial speed for the Earth. I currently have it set so that the distance between these two objects is equal to the radial distance. And so if I take and realize that it's going to take 1 year for this thing to go all the way around. So 2 times pi times the Earth distance from Sun divided by the time, which it is 1 year. And it's handy to go ahead and print this off and make sure that it makes sense. So the print command is just print parentheses around whatever variables you want to print. So I want to print Earth speed and make sure that my results are what I would expect to get over there. All right. So I've created the Sun and the Earth, and you'll notice that the Earth has a couple of additional properties. Both the Sun and the Earth, I've given them mass, but the Earth also has a velocity as well as a force vector. And then I want to actually have the sphere lay down a trail as it moves, and so this make trail equals true will lay down a trail as that object is animated with its motion. All right, so as long as the current time is less than 1 year, then this is going to run through the while loop 300 times per second. And again, don't forget to increment your time. Whatever you are checking up here, make sure at some point in time that's going to evaluate to false. Otherwise, you will get into an infinite loop. And I find it's really handy to define this R vector. Before I get into calculating the forces, let's just run it and see what happens. Make sure that we get what we would expect. So the Earth has some initial velocity, and it should be moving. Oh, I know why it isn't, because I set that to 0. We needed to fix this. Let's just leave it at that for the moment. Let's see if we get, there we go. It's moving in a straight line as we would expect. Now, we need to go ahead and calculate what the force is. So I can just use the Newton's equation for universal gravitation, negative g times the mass, the Sun's mass, sun.mass, times Earth.mass divided by, now I just defined this R vector up here. I can find the magnitude of a vector using mag. So mag parentheses r gives me the magnitude of that vector. Now, do not use the caret symbol for powers. That's actually, it's a bitwise operator. It won't give you an error, but it will give you results that are really funky. To denote powers, you use a double asterisk. So to square something, mag double asterisk 2 will square it. And then we need to multiply this by the unit vector. You can either use the command hat or normal. I'm sorry, norm. They're the same thing. I like hat. So that should update the force, and then I need to go ahead and update the velocity. So the new velocity is the old velocity plus the force on the Earth divided by the mass of the Earth times my time step size. Time step. Let's see what we get. Now, it doesn't quite go all the way around, so something's not quite perfect. It's a question of, is my starting speed not quite right? Maybe it's a numerical issue. Let's take a look and see what happens if we go around more than 1 year. Let's go around 5 years. So while my current time is less than 5 times 1 year, and so we don't have to sit here all day, let's go ahead and up this to, say, a rate of 3,000. Now, it appears to be spiraling outward. And it turns out it has to do with how we are actually solving these equations of motion. What we've been using is what's sometimes referred to as the Euler method for updating our positions. We're going to go ahead and use Euler-Kromer, or the modified Euler, which is a surprisingly easy method. What I'm going to do is copy the code and paste it down here. That way we've got the code up above working, and we can go back to it if we want to refer it. So let's just go ahead and double check that everything is copied correctly and working, and that looks good. Now, a lot of times students will accidentally discover the Euler-Kromer method, because if all you really need to do is switch the order in which you update your position and velocity. So here, when the Earth's position is updated, it's using the velocity from the previous time step. If, however, I put that line after the velocity, and we go ahead and run it, we can see, we zoom in a little bit, you'll notice now that we don't have that spiraling anymore. And so the Euler-Kromer method will give us much better results. However, it's useful to show the Euler method so that students get an understanding of some of these different methods and how they can impact the results that you get. And it helps students distinguish between an error from something that they've entered versus a numerical error. And there you have it.